So this might be a little bit of a long one because we're going to be going into the normal curve. I was telling somebody recently that we're going to spend like 15, about 45 minutes on videos on this. We already have over 15 minutes in the first one, the preview, but I might split this up into two videos. And the reason why is because there is so much information about the normal curve that's very important to know and understand, especially just understanding what it means to be normal, what it means for a graph of frequencies to be considered symmetric and is it actually normal? There's a lot of information, and I spent literally a year taking graduate classes about this, whereas we get to spend 45 minutes. So hopefully, if you have questions, you are more than welcome to ask. And I want to point out that this is a contemporary math class, so we're doing a survey of a lot of different things, which is very different from what you would do if you took elementary statistics, which would go a lot more into these ideas. And so we're just kind of scratching the surface. And so if you are interested in statistics or you're in a field like potentially maybe nursing or psychology, those you might end up taking a statistics course. And so hopefully you find this interesting. I think it's fascinating. So we're going to dive right in and we're going to look at just distributions in general. And so these are displays of different types of distributions. The displays are frequency tables or frequency charts. You can think of them as histograms, right? Because the bars are touching. And we have our data values here, and the number of times they show up is the frequency. And so there are different types of distributions. Now this distribution is called rectangular because if you see all the values, they all show up the same number of times, and so it makes a nice rectangular shape. J-shape is if you have literally these like J's. So the values and the frequency are increasing or decreasing, starting from the highest and going down to lowest, or starting from the lowest and going up to the highest. Okay, so these are not bell-shaped, they are not rectangular, these are J-shaped. And then we have what's called bimodal. Okay, now remember, modes, when we're talking about measures of center, are our values that show up the most often. So in a frequency table, those would be the bars or the bar that's the highest. Those would be our mode values. Okay. But in a bimodal, bi is the prefix that means two, like a bicycle has two wheels. Okay. So this graph has two modes. Okay, they're not perfect, they're not exactly the same, but they're these dips up. It's almost like a camel back that has two humps instead of one. Okay, and so we call that bimodal. So now we're going to look at these and we're going to identify the mid-range and the mode of each distribution. So add the highest and the lowest and divide by 2. So highest and lowest divided by 2 for the rectangular one, that's going to be right there. And then if you look at this, the frequency is all the same for all of the different classes or all the different values, and so therefore there is no mode. J-shaped, if we add the highest and the lowest value together, and then divide by 2, we get this number right here in the middle. Same thing here. But the difference is the modes. So if it's constantly increasing, like the one on the left, my mode is at this highest value or highest class, whereas on the right-hand side, it's the lowest value or the lowest class. So essentially for mode, we're looking for the highest bar. We've already discussed that a bimodal distribution has two modes. You can see them in the drawing. Now this one is higher, so technically it has a higher number of frequency or a greater frequency, but we would consider this to be bimodal because there are the two bumps up in the frequency. Now the mid-range though is add the highest and the lowest, divide by 2, so that gives us a value right in the middle in between those two. And then the modes we've already addressed. Now, The next question is each of these graphs, are each of these graphs symmetric? And if I look at these, the first one is symmetric. It's the same on the left hand as it is on the right hand. These are two separate graphs. They are not symmetric. Okay. The bimodal is not symmetric. Okay. One other thing you need to know about bimodal distributions is that oftentimes it's an indication that you're dealing with two very distinct populations. So the example in the book that they give you is like if they polled women on their weight and men on their weight, there might be a much lower frequency on the women's weight than there are on the men's, or vice versa. Who knows? So just be aware that oftentimes if you have a bimodal distribution, it's an indication that the populations are very different, but they're all included in the same data. Next, we're going to look at distributions that are skewed to the right and skewed to the left. So here's how I remember this. So when we look at these distributions, they're either going to be as a histogram or they're going to be as a curve like this. And essentially it's something that has a tail. And sometimes the tail is very obvious. Like that was a bad example. But it might be like long tail on the left and then a bump up. I can't get this right on here. Hold on. Like a really long tail. If the tail is on the left, it is skewed to the left. If the tail is on the right, it's skewed to the right. Okay, so that's literally how I remember it. Where is the tail? Tail on the left, skewed left. Tail on the right, skewed right. And then last but not least, we have this beautiful normal curve, also called a bell curve because it has a bell shape to it. It's symmetric. So it's the same on the left-hand side as on the right-hand side if we were to think of this as being like a mirror. Okay? Now, a lot of our graphs that we might see might not be perfectly normal, but if they are approximately normal, we can still use the same principles when looking at that data. So looking at these distributions, we can look at where the mid-range is and the mode. So in this case, the mode is the highest, so I'm going to point to that in red. And then the mid-range, add the highest and the lowest, divide by 2. Highest and lowest, so lowest and highest, divide by 2. Then we can look at these and say, are they symmetric or not? So the skewed graphs are not symmetric. If I were to find the middle point here where the mid-range is and fold it over, they wouldn't match up. Same thing on this one. But in a normal distribution, they are symmetric. And one thing you should know is that we have the mid-range right here, but in a normal curve, this is also where your mean is. So if you have a symmetric distribution, then the mean is at the point on which it's like the symmetric point, the line of symmetry. One thing to note is that in a perfect normal distribution, the mean, the median, and the mode all have the same value. So this picture here shows us an example where the mean, the median, and the mode would all be the same. The reason why we focus on the normal distribution is because many sets of data are normally distributed or very close to being normally distributed. And because of that, we can use inference to make predictions about the mean of the population. So if I can get a good sample, non-biased sample, that represents a population and I can find the information about the sample, we can then make inferences about what that means for the population. There are many different sets of data that are closely or very closely modeled by normal distributions. It could be heights and weights of males, heights and weights of females, the weight of watermelons, the GPAs of students. Lots of things are often could be modeled with a normal distribution and then could have predictions made about them based on a normal distribution. The book has like a nice little summary, and it tells us that the normal distribution is often called the normal curve. The normal curve is bell-shaped, it is symmetric about the mean. The mean, the median, the mode of a normal distribution will have the same value and all occur at the center of that normal distribution. So in a perfectly normal distribution, that's what we should see. Now, when we see displays of the normal curve, oftentimes we see it like this, but it could be have a lower frequency, but still be symmetric. This is not perfect, bear with me. Okay, it could also be taller and skinnier. Okay, now with the normal curve, when we draw it, we don't touch on the x-axis. We can get really close to it, but we don't touch. So here's that little summary about the things that we need to know about a normal distribution. Again, it's often called a normal curve. It's bell-shaped and symmetric around the mean. The mean, the median, the mode have the same value, and they occur at the center of the distribution. This is a drawing of a generic normal curve. We have mu, which would represent the population mean. At the center, that's that axis of symmetry, which tells us that 50% of the data values lie on this side and 50% of the data values lie on this side in a normal curve, in a normal situation. The next thing that's interesting about normal curves, and this is the empirical rule, essentially it states that these tick marks underneath show us 1 standard deviation, 2 standard deviations, and 3 standard deviations away from the mean. And so like this right here would be mu minus the standard deviation. Well, in a population that'd be sigma. So, and then this is mu plus sigma. Whereas this would be mu minus 2 sigma because it's a second standard deviation away. And this one's u plus 2 sigma. And then here we would have mu minus 3 sigma, mu plus 3 sigma. Again, because we're dealing with mu and we're dealing with population standard, and we deal with the population mean and the population standard deviation. But anyway, the rule states that 68% of the values in the data set lie within 1 standard deviation from the mean. That's a big chunk of the data. Then the second part of the empirical rule tells us that 95%, so I'm going to shade this in red and say that this is representing 95% of all the data lie within 2 standard deviations of the mean. And so that's within 2 in both directions. So that means from u minus 2 sigma to mu plus 2 sigma, that gives us 95% of our data values lie within that range, okay? Which means that the last part of the empirical rule, and this one's really intense, it says that within 3 standard deviations with around the mean on both sides, 99.7% of the data will lie between those two values. Okay, and so that means that if anything is past that, it's very, very rare. Here's the empirical rule just written out in words. We saw that 68% of the data lie within 1 standard deviation, 95% lie within 2 standard deviations, and 99.7% of all the data lie within 3 standard deviations of the mean. So I learned this rule as the 68, 95, 97, 99.7 rule, but it's called the empirical rule. The book has an example where you apply the empirical rule. Their example is that there are heights for females that are the same age are normally distributed. So the heights are normally distributed. If you take a random sample of 500 females, Determine the approximate number of females in the sample who are expected to have a height that's within 1 standard deviation of the mean and within 2 standard deviations within the mean. So essentially we have 500 women or 500 females that are surveyed, and we get their heights and we get this frequency, and it's around the mean. Okay, because it is normally distributed. And so it's asking how many of the females will lie or have heights that lie within 1 standard deviation about the mean. That means going both directions. So we know that this, by the empirical rule, represents 68% of our data. So that means if I find 68% of 500, that will tell us how many females will have heights within that range. And so, and remember, this mu down here is telling us the average height. Okay, so these are representing height values. That's our variable that we're looking at. And our mu value is telling us the average of the heights, or the mean. And so when we find 68% of 500, that's going to tell us how many women or how many females had heights within these two height values. Okay, so 68 times 500 is 340. Okay, now based on the empirical rule for the second part of the question, how many of the females have heights within 2 standard deviations of the mean? So that's 2 standard deviations. We know that that is representing 95%. Remember, this 68% isn't included in that. But we have the extras over on the left side and on the right side. So this should be 95% of the females who reported their height will lie within that region. Their data will lie within these two heights here. So then you find 95% of 500 and you'll have the answer to that. 95% of 500 is equal to 475. Okay, that's almost all of them. Almost all of them will be within 2 standard deviations of the mean. But that means that there are a few who are very, very tall, and there are a few that are very, very short. Nothing's wrong with that. It's just the way that heights are distributed. So let's look at an example. Warm-up 1. We're going to assume that the mathematics scores on the SAT are normally distributed. The way we write that is we say X, which is representing the scores, is normally distributed with a mean of 500 and a standard deviation of 100. So we write it out this way. This is just a way to say it's normally distributed about the mean and the standard deviation. Okay, so we are going to label the scores that are 1 standard deviation away, 2 standard deviations away, 3 standard deviations away from the mean. So our mean, they told us what our mean is. So this mark right here representing scores is 500. So 1 standard deviation to the left is 500 minus 100. So that's going to be 400. And 1 standard deviation to the right is adding that standard deviation. So this would be 600. 2 standard deviations would take the mean, 500, and subtract 2 times the standard deviations, or 2 times 100. So that gives us a value of 300. And over here we'd have 700. And 3 standard deviations away would be at 200 and at 800. Okay, so then the question is asking us, what percent of the students who took the test have a mathematics score above 700? And so this is where we use the empirical rule in a very interesting way, because the bell curve, the normal curve, has to add up to 100% of the data. And so if I know that 95% of the data lives between those 2 standard deviations, okay, that means that 5% is divvied up amongst both sides. But it's normal, so it's divvied up equally. So the remaining 5% gets divided equally into these 2 parts. So on this side, we would take the remaining 5% and divide it by 2, so we end up with 2.5%. And on this side, we would have 2.5%. And so we can actually see what percentage of students who took the test have a mathematics score above 700. Well, that's going to be in this area over here. Okay, so that's going to be 2.5%. How many people have a score that's below 400? So let's take a look. I'm going to clear out some of this. Okay. Let's draw a mark at 400. 400 is 1 standard deviation away from the mean. And we know that in this region, 68% is represented. 68% of the data is represented, which means 32% remains. And so if I take 32% and split it up amongst the two other regions that we haven't shaded, 32 divided by 2 is 16 and 16. So essentially what I'm doing is 100 minus the 68, which gives us 32, and then we take that and divide it by 2 to spread out to the two remaining sections. So when they ask me how many people scored below 400, that's talking about the scores in this region, which represents 16% of the scores based on the empirical rule. All right, last one. Let me do the erasing again. Boop, boop, boop. Okay, what percent of the students who took the test have a mathematics score between 300 and 600? Okay, so let's think about this. 300 and 600. Okay, so we know that within 1 standard deviation we have 68%, but this is symmetric, so that can be divvied up into each part. So this is 34% and this is 34%. Okay, now we can do the same thing with the second standard deviation. That represents 95%. And so from here, if all of this is from 300 to 700 represents 95%, then half of that would be 47.5 on this half, from here to here, and on the other half, 47.5. Because when you add those up, you get 95. So the reason why this is helpful is because if I'm looking at the scores that I'm going to highlight, let's do it in yellow, the scores between 300 and 600, I want to add together my pieces. So this piece right here is 47.5% of the data, and this piece right here was 34%. So I would take those two pieces, 47.5%, and add it with the 34%, which gives me, I'm going to add it by hand. We have a calculator, so we can use it, but I'm just going to do that by hand. That gives us 81.5% of the scores lie between 300 and 600. So the empirical rule is really helpful because it lets us kind of break these symmetric pieces into smaller pieces so that we can find out what percentage of the data lies between certain values. I think that's really interesting, especially in terms of test scores. Okay, I'm going to stop here on this video, and we'll do one more video with a few more examples and z-scores, which are super important, and then hopefully that will be sufficient.